All right, guys, good morning. Happy Monday. We're almost winding down. Um, so, kind of what's going to happen with y'all's kind of last week, what we're getting into. So, in Canvas, there is kind of a final exam review. That's kind of where we're going to be focusing. So second period, your exam is a week from today. So your exam is on Monday, which is the 24th. This video is also for Ms. Kincaid's fourth period. Y'all's exam is going to be on Wednesday, the 26th. So kind of the last teacher-made exam day. What you'll find in the final exam review, y'all bear with me, we're missing a bunch of people, so they're popping in through the lobby. There's the final exam review. This kind of has practice questions that are split up by unit. So kind of things to make sure that you know how to answer these types of questions. These are types of questions that may come up, how we'll ask you about different topics. This Chem review presentation, the second one, that's what we're going to be going through the next couple of days together. Just kind of like unit one. Here's kind of the things that we did, the things to look back at and remember, and we'll go through all the different units that we did. You guys get to move a little bit slower than first period since y'all exam is not till next week. There's some other review resources. These crash courses are kind of like one-pagers that my friend Miss Marsh over at West made a couple years ago. So that might be a good thing if you're like, I just don't remember what chemical reactions are. I need to go review those specifically. You can spend a little bit of time on those. This final exam review is optional. We're not taking it up, but that would be very beneficial to you, especially if you're like, I have no clue what's going on. I don't remember anything from February, and now I'm going to be tested on it. You know, just kind of going back and flipping through those. This week and on your days that you're not taking your exam, you'll have time if you owe me work to get that made up. If you're working on the remediations for the quiz or test, you'll have a chance to do those as well. There will be a chance for you guys to do kind of an, I'm going to call it an independent study of gas laws. That will be an opportunity to replace your lowest homework grade. So if you like forgot about something, did it super late and it was halfway done, you got a 25 and you want to do this and replace it with 100, that's possible. So that'll be posted shortly. I have to record a video for it. But that stuff will kind of come up, but you kind of have time to work through what you need to, whether it's studying for your exam, catching up on makeup work, or doing some of those remediation assignments. So we're going to go ahead and get started. That way I can let you guys go to kind of work on that stuff that you need to. We're going to be going through this review presentation this week only. That way I don't have to record separately for fourth period versus second period. So we're going to spend 4 days going through this. It's 34 slides. So we're going to do about 8 or 9 slides a day. So very manageable, not going to be a ton. But we'll kind of talk about, like I said, in each unit, we'll kind of talk about those big topics, things to go back and review, things to make sure you're able to do calculations with, stuff like that. So we're going to go ahead and start off with our introduction to chemistry. This is our first unit that we started back in January. So it's been a long time since we've done some of this stuff. Just some things to review and look over. General safety rules. These were pretty self-explanatory. This was stuff that we did when we were talking about kind of lab safety and stuff like that. Pretty much anything that happens, call the teacher over. So like if you spill chemicals, call me over to figure out how do we clean this up? Can we just use paper towels? Do we need to use the sand bucket? Things like that. If you cut your finger, what are you supposed to do? So call me over. We'll make sure it's cleaned properly. bandaged up, all of those things. So kind of review those general safety rules. Unit 1 was mostly review stuff from previous science classes. So we did go over how you change metric units. So that was using those metric prefixes. So that was using the King Henry, died by drinking chocolate milk. So there were larger units and smaller units, but these are kind of those main ones that we deal with. So we've used some of this more recently, like having to change from milliliters to liters, things like that. But remember, the base unit, excuse me, is anytime that you only have a single letter unit. So that's going to be like meters, grams, liters are all going to be that base unit. So if we're changing from meters to kilometers, we move the decimal 3 spaces to the left. If we're going from liters to milliliters, we move it 3 spaces to the right. So remember, that was just how many times you have to move the decimal to convert from one thing into another. Don't worry about sig figs. So I know some of y'all are going to be happy about not having to go back and review those. But another thing we did in Unit 1 that was still review was beware of writing numbers in scientific notation. So remember, a lot of times when we do math, our calculator will give us one answer, but that might not match the answer choices, because a lot of times our answer choices are written in scientific notation. So remember, scientific notation, you can only have one digit in front of the decimal point, and it's multiplied by a power of 10, and the exponent tells you how many times you move the decimal place. Remember, large exponents, those positive exponents, mean it was greater than 1, so generally a large number. Negative exponents indicate that the original number is a decimal number. So that's kind of how you can go back and forth. Okay. All right. Also in Unit 1, we dealt with parts of the periodic table. So we actually did where you had to kind of label and color in the periodic table, looking at the different sections, some of the different group numbers, just kind of being able to navigate your way around and identify different types of, or different parts of the periodic table. So we had our representative elements. Remember, those were our group A elements. So on our periodic table, remember up at the top, each column has a label. So the label is kind of going to help you know which group it is. So our group A elements are those first 2 columns on the left and the last 6 on the right. So it's like 1A, 2A, 3A, all the way up to 8A. So this does not include those transition metals that are in the middle. Then we have our transition metals, which are our group B elements. So remember, that's kind of that drop-down bridge that connects the 2 sides of the periodic table. Up above those columns, it does have the letter B up above them. So it starts at 3B, goes up to 8B. There's like 3 8Bs though, and then it goes 1B, 2B. So it is kind of labeled there. With our metals, metalloids, and nonmetals, remember there's kind of that bold stair step on our periodic table towards the right side. Metals are to the left of the stair step. So that makes up 2/3 of the periodic table are our metals. I'm going to skip down to nonmetals. They're to the right of the stair step. So that top right-hand corner. And then metalloids, these are the ones that are on the stair step. So anything touching the stair step, with the exception of aluminum, is a metalloid. So remember, metalloids are kind of those hybrid where they have properties of both metals and nonmetals. So these are ones that can be like semiconductors and things like that. Then we went into some of our specific group names. I'm going to scroll down just a little bit. So we had our alkali metals. This is that column all the way to the left. That's our group 1A. So that includes like sodium, potassium, stuff like that. Right next to them are our alkaline earth metals. This is that group 2A. So that's going to be stuff like magnesium, calcium, strontium, barium, kind of going down the list. Skip over towards the right side of our periodic table and we'll find our halogens. That was in group 7A. So those are some of our diatomic molecules, like the fluorine, chlorine, bromine, iodine, are our halogens. And then we have our noble gases. These were the group 8A. So these are the far right column. So that's like the helium, neon, argon, krypton, all of that stuff. So remember, noble gases are fairly stable. They tend to not react with anything, with the exception of some of those larger ones. Whereas alkali metals tend to be the most reactive metals. Halogens tend to be the most reactive nonmetals. And then we also had our inner transition metals. These are those bottom two rows. So these are the two rows at the bottom that are separated from the periodic table. But remember that these are our inner transition metals because they insert into our transition metals. So these are the lanthanide and actinide series. So these are actually in the 6th and 7th row of the periodic table. But the reason we separate this is that your periodic table can fit on one page. If not, your periodic table is going to be like a mile long and go all the way across with those 14 kind of squeezed in the middle. All right. Also in Unit 1, we talked about matter a good bit. So looking at the different types of matter there were, and different types of substances overall. So matter is split up into either mixtures or pure substances. So mixtures are just physically combined. They're kind of stirred together. So mixtures can be physically separated. So that means that these aren't actually bonded together. We can simply pull them apart. So this is where we might actually be able to pick through with our fingers and separate them. We might be able to distill them or boil one of them off. We might even be able to just put them through a filter to separate them. We had two different types of mixtures. So we had the homogeneous and heterogeneous. So remember, those are prefixes that we used in biology as well. So remember, homo means same. So this is where if we look at this mixture, everything looks the same. We say it's fairly uniform. So that means even though we know it's a mixture and there's multiple things in there, we can't actually see them. We can't tell one part of the mixture from another part of the mixture. So some examples of this, something like soda. So if you were to look at the ingredients in soda, there's like water, carbonated beverage, there's probably some coloring, flavorings, there's sugar, probably types of syrups, anything like that. Well, whenever you pour it in a cup and you're looking at it, you can't see all the different ingredients. It all looks the same. Same thing whenever we're doing like lab. We did several labs with like silver nitrate solution. You can't look at that and see, okay, where's the water and where's the silver nitrates that's dissolved in it. It all looks like one substance. Whereas the heterogeneous one, so hetero means different. So here you can actually see all the different pieces. So we say this is non-uniform because you can look at it and pick out the different pieces. So sometimes they're just simply large enough that you can see them with the naked eye. Sometimes these will separate into layers or things like that. So some good examples we used were like trail mix. So trail mix, you know, if you buy them at the store, one brand of trail mix might have different ingredients than another brand. If you pour it all in a bowl, say that you don't like raisins, well, you can pick out like the cashews, the almonds, the peanuts, the M&Ms, the raisins. You can separate out the raisins so that you can eat the pieces that you like. Another example, we said things that like separate into layers. So this would be stuff like Italian dressing. So some salad dressings and stuff like that, it says like mix or shake before use. And that's because a lot of times the different components will settle out. Italian dressing is oil-based, but it does have other stuff in it. If you leave it sitting in the fridge, you pull it out, you'll see all the different layers. So you have to shake it up and mix it before you put it on your salad, or else you're just going to get oil versus all the different spices and things that are in it. So then our other type of matter is pure substances. So pure substances are categorized as either elements or compounds. So one thing about pure substances is these cannot be physically separated. So they have to be separated chemically if they can separate at all. Elements cannot be broken down any further. So like the smallest piece is an atom, and we can't split the atom any further. That's as far as we go. So this is going to be anything off the periodic table. So it could be like iron, neon, oxygen, something like that. Whereas compounds, so remember these are elements bonded together. These can be separated, so can be broken down. But they have to be broken down chemically versus physically. So we actually have to do something to break apart that bond to separate into the elements. So this is where we might heat something up, we might burn it, we might mix it with another compound to make those elements split up. So compounds can be separated into elements chemically. So you can't simply pull them apart and break that bond. It has to be like heated or burned or something like that to make them split apart. Unit 1, excuse me, also talked about states of matter. So remember our states of matter were like solid, liquid, gas. We talked about solids, remember have the kind of set shape and volume. You can't like push down on your desk and make it any smaller. It's kind of that set shape and volume. Liquids, remember that they have a certain volume, but they can change their shape depending on what their container is. So if you get a can of soda, it's normally 12 ounces. Whether it's in the can, you pour it in a cup, or you spill it on the floor, it's still 12 ounces, but the shape can change depending on what it's in. Whereas gases, both the shape and volume can change depending on what its container is. Okay. Unit 1, we also talked about physical and chemical properties and changes. So this was whether we were making observations or actually changing the substance. So physical, whether it's properties or changes, the composition stays the same. So whatever that element is, or whatever something is made up of, stays the same. So you're not actually changing the chemical makeup of the substance. So these are observations you can make. So you could look at something, tell what color it is, tell if it has an odor. You could melt something. So like if you melt ice, it just went from being solid water to liquid water. You didn't actually change what the substance was. So any phase changes are going to be physical. So we said it could be melting. You could observe the color. You could observe if it has an odor, if it has a density. So you can measure something's density. Sorry, I cannot spell today, y'all. I'm on the struggle bus. So you could also measure something's density without changing what it is. Some of those physical changes are things that might alter the appearance, but it's still the same substance. So those are going to be things like if you cut something or if you bend it, you might alter the shape, but it's still the same substance. So if you slice a tomato, it's still a tomato. It's just now in pieces. You didn't actually change what it was. Another good one is if you dissolve something. So say that you have a sore throat and you have to gargle salt water. You dissolve salt and water. It's still salt and water. It's just now mixed together. So you didn't actually change the chemical substance that you have. Whereas chemical properties and changes, these are going to alter the composition. So this is actually going to change what the substance is. It's no longer going to be the same substance. So a lot of times these properties are not observable without changing the substance. So we might know that something has a certain property, but if we observe it, it actually changes it. So this is where we might describe stuff as being flammable. So we know it's flammable, we know it can catch fire, but if it does catch fire, that's a chemical change. We might also describe something as being corrosive or combustible, things like that. So you can't observe those properties without actually changing the substance. All right. And here's one thing. This was literally one slide in Unit 1, and I kind of told you if you don't write down anything else, write down this slide. There are some common chemical tests, in particular looking at colorless, odorless gases. So this is where we kind of can tell the difference between hydrogen, oxygen, and carbon dioxide based off of how they react with a flame test or how they react with lime water, depending on what the substance is. So with oxygen, oxygen is one of the parts of the fire triangle. That's something we deal with in forensics with arson. But a fire needs oxygen in order to actually burn. If there's no oxygen, there's nothing fueling that flame. So since oxygen fuels a flame, it will actually ignite a flame. So if you were to blow out a match, stick in oxygen, it will actually reignite and come back to life. In terms of hydrogen, hydrogen is combustible. So combustion reactions are like explosions. So whenever hydrogen comes in contact with flame, it will be a combustion reaction. It will be a small explosion. So you would actually hear a loud pop, possibly a flash of light, depending on the size of the reaction. And then carbon dioxide. So carbon dioxide was one that we had two different tests for. Carbon dioxide is the stuff that is in fire extinguishers. So carbon dioxide actually extinguishes a flame. It displaces the oxygen. So since there's no oxygen, a flame can't burn there. So like I said, this is what's in fire extinguishers. It kind of starves the fire from oxygen, which lets it kind of go out. We may not have done this a while since COVID, but like if you're blowing out birthday candles, you breathe out mostly carbon dioxide. So you're pushing the oxygen out of the way, which is what allows the candle to go out. So if you were to stick a lit match in carbon dioxide, it would extinguish, it would go out. Carbon dioxide also had a test for if you combined it with lime water, it would actually become like very cloudy or milky, and it actually produces a form of chalk. So just know that carbon dioxide turns like white or cloudy with lime water. All right, calculations that we dealt with in Unit 1 weren't terribly bad. Everything kind of had a set formula. You plug in, solve for X. With Unit 1, we dealt with density, so that was one of our physical properties. So this is a formula that's on our reference sheet, is the density is equal to mass over volume. So there are densities on your reference sheet on the front page. So this is somewhere where it might give you a mass and want to know what the volume is. And you have to remember to use the densities off the reference sheet. Another way that we set this up that you might have seen is the density triangle. So we said density is mass over volume. If we draw a triangle and then put lines separating our different variables, this is just kind of another way to rearrange that density formula. It's like if we're solving for volume, cover up volume, and we're doing mass over density. We said density was mass over volume. If we're solving for mass, cover up the M, and we're doing density times volume. So it just kind of helps you rearrange equations as needed. And then we also went over changing temperature to Kelvin. So remember, Kelvin temperature is equal to the degrees Celsius plus 273. That's one that we dealt with a little bit, but since we skipped gas laws, we didn't have to deal with it too much. If you kind of do the gas laws independent study, the homework replacement, you'll be using this a lot, changing from Celsius to Kelvin. Unit 1, we also did percent error. This is something that we do mostly in a lab setting to see kind of how far off we are from what we should get. So this is one where percent error is the absolute value of the actual minus the experimental value divided by the actual value times 100. So this is if we were in lab trying to find the density of something. Density is kind of a known accepted value for every substance. So say we were finding the density of a piece of aluminum. Our actual value would be the value of density from our reference sheet for aluminum. We have our experimental value of we measured the mass and the volume and found density. That's what we would plug in. So we would see how far off from the expected density are we. All right, then we got into Unit 2. I kind of have 2 and 3 together, but it's kind of separated with 2 coming first. So Unit 2 is where we started talking about that kind of basic atomic structure and nuclear chemistry. We're kind of going to talk about basic atomic structure, and then we're going to stop before nuclear. That's kind of where we're going to pick up tomorrow. So remember, if you're looking at an element on the periodic table, the individual box on the periodic table, it gives you that atomic number. The symbol, most of the time, it's from the English version of the name. Sometimes it's from the Latin version. Remember, the symbol's either going to be one letter or two. It always starts with a capital letter, though. If it has a second letter, that second letter is lowercase. So make sure you kind of distinguish between capital and lowercase. It gives you the element name, and then it gives you the average atomic mass of that substance. So we're going to go over calculating average atomic mass in a little bit too. Okay. And with basic atomic structure, we looked at isotopes. So remember, isotopes are atoms of the same element, but they have a different number of neutrons, which gives them a different mass. So with isotopes, we kind of introduced mass number. So this is how we knew that it had a different number of neutrons and a different mass. So mass number is our protons plus our neutrons. So it looks at the mass of the nucleus, because those are the two particles inside the nucleus. Two ways that we see isotopes written are these two isotopic notations with the AZX form and the kind of element name -A form. So remember, A is our mass number. So A is protons plus neutrons. The Z is our atomic number, which is our number of protons. And then the X is simply our symbol. So the AZX form gives you the mass number, the atomic number, and the symbol. The other form with the element name A, it tells you the name of the element and its mass number. One thing we did with isotopes is we actually looked at where these different subatomic particles were and how many of each subatomic particle we have. So in terms of subatomic particles, you're going to be able to tell where their location is, what their charge is, and how many of them you have. So that's something that we focus on heavily in Unit 2. So remember, protons is kind of the identity of the element. That's going to be equal to the atomic number. So like iron is number 26, so it has 26 protons. Protons are located in the nucleus. And remember, protons are positive, so they have a +1 charge overall. In terms of neutrons, remember, neutrons are also in the nucleus. And these have a neutral charge. These have no charge. To find number of neutrons, we have to use our mass number. So kind of rearranging this, we'll do mass number minus atomic number, so minus the number of protons to get the number of neutrons. In terms of electrons, it depends on if it is neutral. So if it's neutral, it's going to be equal to the atomic number, or it's related to the charge. So it will be the charge minus the number of protons. So if it's neutral, remember, protons and electrons are the same. But whenever we have an ion and something has a charge, that means that the number of electrons change. We can't change the number of protons, but we can change the number of electrons. Electrons are not in the nucleus. They're outside the nucleus in the electron cloud. And remember, electrons are negatively charged, so we say that they have a charge of -1. And calculation-wise, so we said average atomic mass. That was that bottom number on each box in the periodic table. We calculated this based off of our isotopes. So for each isotope, we had to do the mass of that isotope times its percent abundance. Remember, this is a weighted average, kind of like your grade is. Not everything is identical across the board. You're going to have more of one isotope than another. So for each isotope, we did the mass times the percentage, and then we add our products together. So this is kind of how your grade is calculated, where your test is like 60%, quizzes are 20, and then the labs and homework are 20. So to figure out your grade, you would take your like test average times the 0.60, your quiz average times 0.2, your lab and homework average times 0.2, and then add all those together to get your final average. With nuclear, we also dealt with half-life. So half-life, remember, is how long it takes for half of an isotope to decay. If you've done this in math, depending on which math you're in, they do use the formula of the whatever's left over is equal to the original mass times 1/2 to the number of half-lives. We did it where we kind of use the table. That tends to work more efficiently, depending on what type of question you're given. So remember, for the table, say that we have 100 grams of some isotope, and we want to know how many grams left after 4 half-lives. Now, sometimes it'll tell you like it's been this much total time, each half-life is this long. So figure out how many times it has to cut in half. So remember, at time 0, at the very beginning, we have 100 grams. Well, after 1 half-life, that's going to cut in half to 50 grams. After a second half-life, 50 will cut in half to be 25 grams. After a third half-life, 25 will cut in half to be 12.5 grams. And after a fourth half-life, 12.5 will cut in half to be 6.25 grams. So remember, that's one way that tends to be easier to do half-life, especially if you're given the like beginning and the final amount. That way you can figure out how many times it's split in half. And that should lead into nuclear, which is where we're starting tomorrow. So that's where we're stopping today. That got you through all of Unit 1 and most of Unit 2. Like I said, in Canvas, you do have that kind of final exam review that you can, even if you don't fully do it, skim through and be like, yes, I know how to do these questions. I'm not so sure on this one. I need to review this concept a little bit more. That'll just kind of give you an idea of where you may need to focus some of your study time. And honestly, you either know how to do some of this stuff or you don't. You have a week to figure out how to do it if you don't know how to do it. So that's where you can utilize your class time. Say, look, I know this stuff in Unit 2, but I'm not sure how to do this. I'm not remembering this piece. And those are things that we can kind of talk through and I can help you with. Your exam will be during class on your exam day. So like I said, second period is Monday. So I'll open it at about like 9:05. Give everybody in class a couple minutes to get in and get settled. You should have plenty of time to finish it in class. It's 50 multiple choice questions. Some are math based, some are not, but that should be plenty of time to get through it during class. That way you don't have to worry about, going through all 4 classes. Maybe you have work after school and all that stuff. That way we can kind of go ahead and get it taken care of. That's it for today. So I'm going to let my guys at home go. I'll stay logged on if you have any questions. But you kind of work on what you need to work on, whether you're reviewing, doing makeup work, or working on remediations.